In section 4.1, we're going to take a look at Newton's method. In Newton's method, the goal is to solve certain types of equations, specifically types of equations that we don't have a really good algebraic method for. So for instance, we see this 5th degree polynomial here. If I didn't know factors of this 5th degree polynomial, it would be pretty hard to solve this algebraically. The same is true with this equation. We have cosine of x is equal to x. There's not a really great algebraic systematic method for an equation like this. Polynomials, generally we have methods for, but when we mix and match lots of things like cosine x equals x, or even in some ugly polynomials, it might be tough to solve. Newton's method isn't actually solving the equation, but rather it's going to give us a good approximation. You can see in the previous example, cosine x equals x. To get an exact answer might be incredibly difficult. In fact, it likely is going to be an irrational number as the answer. But if we're okay with approximation, then we can solve it at least up to a certain spot, meaning we can solve it rounded to 3 decimal places or something like that. The way Newton's method does this is through tangent lines. We're going to approximate a solution to an equation using tangent lines. That's essentially what Newton's method is wanting us to do. So here's the basic idea. We're looking for the roots of a function. So we set up a function and we're trying to find out what inputs give us 0. We start with a guess. Our initial guess is called x0. It's some x value, and the sub-0 just means it's our initial starting guess. We're going to calculate the output of that function. If the output is 0, then we're done. We've found the root. If not, we can find the tangent line through the point x0, comma, f of x0. And that tangent line must cross the x-axis closer to the actual root than x0 does, or x0 does. And that point where the tangent line crosses the x-axis is going to be a better approximation than the x0. And you can repeat that process over and over and over until you get a really good approximation. Here's a visual of what's going to happen. Let's say this blue curve is our function f of x. And I start at x0, at this guess. I'm going to calculate the point, the y value of the point by plugging in this x0 into my function. This is obviously not crossing the x-axis at that point. So then I calculate a tangent line. I look for where the tangent line crosses the x-axis. This x1 is going to be a new value, and it's actually going to be closer to the root than x0 is. And then I can do that process again. x1 isn't a root, so I go look at the point on the function at x1. It's not a root, so I calculate the tangent line, find where it crosses the x-axis, and this next value, which we call x2, is going to be a better approximation. And you keep going and going and going and doing that over and over and over again until you're satisfied with your approximation. So you start with x1 as your first guess, second guess, excuse me, x0 is your first guess, x1 is your second guess, and so on and so forth. You can do that as many times as you want. Now, the key here is finding the next guess, finding the next xn. Let's think about how we do this with x1. A line is going to look like y equals mx plus b. We know, since we're talking about a tangent line, that the slope of that tangent line has to be the derivative of the function at x0. So we're going to have to be able to find the derivative of the function at x0, and that's going to be my slope. If I want to find the value of b, well, that is able to be done by replacing the slope-intercept form with the slope-point form of a line. And so instead of looking at the slope-intercept form, it's a little bit easier if we look at y equals mx minus x0 plus f of x0. In other words, we know the line goes through the point x0 and then f of x0. So the point slope form would be this one. Now I want to find where the line crosses the x-axis. That means where the y value is 0. And therefore, I can replace the y value with a 0. I want to solve now for x1. So what I would do is I would subtract f of x0 from both sides. Then I would divide by f prime of x0. And then I would add x0. And if you solve for x1 here, you get x0 minus f of x0 divided by f prime of x0. Therefore, in order to find the next guess, it's always just going to be this equation here. So this is Newton's method in a confined space. Let f be a differentiable function on interval I containing a root. Choose an initial value x0 as an initial approximation of the root. Then we can create successive approximations with that formula we just found. The next guess is going to be the previous guess minus the function value inserted, the function output of the previous guess divided by the derivatives output of the previous guess, where our input is the previous guess. And we keep doing iterations. We keep doing this over and over and over until we get as close as we want. So Newton's method could go on indefinitely, but we stop at a certain point when we feel we're close enough. So all we need to do is know that the next guess for a root of a function can be found using this formula. And we can do that over and over and over until we get a good enough approximation, at least one that we're satisfied with. We're going to use Newton's method to approximate a real root of the following function. Start the initial approximation at x0 equals 1 and use 4 iterations. An iteration just means that's how many different approximations we're going to use. We're going to go through the process 4 times. Here's our function. Now, before we get started, I'm going to both calculate the function and the derivative because we need the derivative as well. The derivative is 2x plus 2. Remember, we said our initial guess was 1. So x1, our next guess, is going to be x0 minus f of x0 divided by f prime of x0, right? By the algorithm we just saw. I kind of skipped a step here. I should have checked and just to make sure that 1 didn't work. I did that in my head, but I didn't write that down. So if I plug 1 in to the function, you end up with a 1. All right. By the way, if you plug 1 in to the derivative of the function, you get 4. So x0, our first guess is 1. I see that that's not a root because when I plug it into the function, I do not get 0. So the next step is saying, well, what's the derivative there? Derivative is a 4 at that spot. So we take that information and we calculate our next guess. Our next guess will be 1 minus f of x naught, in this case is 1, f prime of x naught. By the way, I keep saying x naught because that's another way of saying x0. So x naught and x0 mean the same thing. When I calculate my next guess, I get 0.75. Let's see if that is a root. If I plug in 0.75 into the function, what do I get out? 0.75 squared plus 2 times 0.75 minus 2 becomes 0.0625. If I plug in 0.75 into my original function, I get 0.0625. Let's plug in 0.75 into the derivative. If I take 2 times 0.75 plus 2, I get 3.5. I want you to take note of what happened here. My initial guess of 1 gave me out a function value that was 1. Notice my second guess gave me out a function value that is much closer to 0. So this is a better guess for the root than this was. Obviously, 0.75 is not a root itself, so we go and do another iteration. Let's go ahead and do that. So instead of, let's do our x sub 2. If we do our x sub 2, that's just the first guess, or excuse me, that x1, 0.75 minus 0.0625 divided by 3.5. I get an ugly decimal, 0.73211428. I'm going to round that right now to 6 decimal places. And then we're going to figure out what the value of the function is at this value. The function evaluated at 0.732143 is actually equal to, when I typed it in my calculator, I ended up with scientific notation that is about 3.1937 times 10 to the negative 4 power, which is like 0.0003197. Notice we're getting closer to 0 as our output. We started with our output being 1, and then we went down to 0.0625, and now we're down to 0.0003197. If we look at the derivative evaluated at 0.732143, I have not calculated this yet, but I will just type it in my calculator. I ended up with about 3.464386 if I go out to 6 decimal places. So our first guess is a 1. Our second guess was 0.75. Our third guess is 0.732143. That's our third guess. Let's do one more iteration. We'll call that, this is probably 3 iterations, although I guess it said 4, didn't it? So I guess we'll do another. I'll do these pretty quick, these next couple. So in this case, we take our x2 minus fraction. What goes on top of that fraction is the function output. What goes on the bottom of that fraction is the derivative. Type that into your calculator. I ended up with 0.732051 when I round to 6 decimal places. I can take that, see if that gives me a 0. It doesn't, but it gives me something really close. I ended up with about 6.66 times 10 to the negative 7th. Again, that's even closer. That's something like that. And then when you plug that into the derivative, we can see the output of the derivative as well. The output of the derivative is about 3.464102. All right. So first iteration gave me 0.75. Next iteration gave me 0.732143. Next iteration, 0.732051. Next iteration, well, let's look at the next iteration here. Take that same scenario and just change our guesses from our second guesses to our third guesses. X3, we saw rounded to 4 decimal places, is right there. minus fraction top of the fraction, bottom of the fraction is this. I'm rounding to 6 decimal places, but if you rounded to more decimal places, you'd probably get slightly better results here, more accurate results. That's okay. When I round to 6 decimal places, 0.732051. Notice what happened here. When I rounded to 6 decimal places, this little bit of change changes this number, but it's less than 6 decimal places. All right. In other words, that 6 decimal places is a millionth, I believe. So it changed it by less than a millionth. So our fourth iteration actually looks like the exact same number as our third iteration because we're rounding to 6 decimal places. But if we would have rounded to more decimal places, if you would have went out to like 11 decimal places, you would have seen a difference. Okay. So just be careful about that. You can see that rounding does matter. And you can imagine that beyond this point, every iteration is going to be the same in the first 6 decimal places. So this is telling us that the first 6 decimal places are always going to look like this. So let's go back over this. We started with an initial value. Our initial value, our function was 1 above the actual x-axis. We want to find the root. So we want to find when this function, when you plug in a number and you get 0. We did Newton's method, and our first iteration gave me out a 0.75 as our x value. That got pretty close to the x-axis. In our second iteration, we got 0.732143. That got even closer to the x-axis. By our third iteration, 0.732051, that got really, really close to the x-axis. So close that when we did the fourth iteration, we got out the same exact value, the same exact number. Now, the reason I chose this function, f of x equals x squared plus 2x minus 2, is because this does have an algebraic way of solving and looking for roots. If I want to find when this function is equal to 0, well, I can simply use the quadratic formula. Opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. And what happens is that you end up with a fraction of -2 plus or minus the square root of 12 divided by 2. If you calculate that, in fact, let's calculate the one where you do the plus. So if I calculate -2 plus square root of 12 and then divide it by 2. So I'm doing the plus version. If you do the plus version, sure enough, you get 0.73205, 1 if I rounded it to 6 decimal places. So rounding to 6 decimal places, we can see we got the same answer using the quadratic formula or Newton's method. And that's the power of Newton's method, that this will give you roots, or at least roots rounded to as many decimal places as we want. We can check on this one that that method actually does result in the right answer. I want to state for the record that this found one of the roots, Newton's method found one of the roots because I started with an initial guess of 1. If I would have started with an initial guess of -3, I would have gotten the other root. So that's what's going on. So that's the power and niceness of Newton's method. What I would like you to do is to use Newton's method to approximate a real root of the function. And I want you to start with an initial approximation of x0 equals -1.5. This time, I want you to try to use 3 iterations of Newton's method to get the approximation. So an x0 of -1.5 and use 3 iterations to get the approximation.